Hello, everyone. This is Mr. Vallejo, and welcome to your science class. Today, we'll be taking a look at scientific notation. So let me go ahead and share the screen with you. It looks like this. Okay, you remember you have these slides in your Schoology or Canvas account, and you can access those slides if you'd like to take a look at them at your own pace. So let's go ahead and get started and learn about scientific notation. All right, with scientific notation, that's going to be very useful for us in the classroom. And in case you have not yet done so, I want to remind you that you'll be taking Cornell notes. So go ahead and set your paper up like this here. Or if you're using the Cornell note template, that also would be acceptable. That would be great. And in fact, I would encourage you to take your notes electronically using the Microsoft Word template. If you want to use this as a Google Doc, then go ahead and take the document and stick it in your Google Drive and convert it to a Google Doc before you start to use it. All right. So what is this scientific notation? Scientific notation is a way to write really big numbers or really small numbers. And so that's what the scientific notation is. So, I remember maybe you remember, the remake of uh, Teenage Mutant Ninja Turtles. Now, see, that was back in the 90s they had that film, but they remade it maybe 10 years ago. And, and on the remake, the smart turtle, what's his name? Leonardo, I think. The smart turtle had a computer strapped to his back, and the other guy, I don't know who that was, had some swords back here. Went like that. It said, Leo, what's the chance that we're going to get out of this alive? And Leo said, 0.0000000003. Ah, if Leo was smart, he would have used scientific notation to tell us, and that would make more sense. And to know that it's a really small number. So if you write this down or type this into your template, by using powers of 10, we can create short versions of long numbers. So whether it's long because it's really, really big, like 100 million, trillion, billion, a number like that doesn't even make sense in my head, but it's a really big number. Well, it'll make more sense if we use scientific notation to represent those really big numbers. Or if you have a really, really small number, like the size of a virus is 0.00000001. How many zeros was that? Well, see, with scientific notation, you can know that. So by using powers of 10, we can create short versions of long numbers. All right, this will be the most important slide for the day. After this, it's basically a lot of uh, examples. Okay, so make sure you get this information in your notes. Rules for scientific notation. All right, so the number that you have, I'm going to my neighbor just to let us know about. My neighbor's like 75 years old. Okay, so the number must be written with what's called the mantissa. The mantissa is a number between 1 and 10. And you can see in the example that we have at the bottom of the slide, it's going to be something like this, okay? This number right here is called the mantissa. Again, the mantissa is a number that has to be between 1 and 10, and it's multiplied by a power of 10. So we always have an x and we have a 10. But this exponent is going to tell us how many zeros we have. So again, it says the number must be written with the mantissa, a number between 1 and 10, and multiplied by a power of 10. So there's your multiplied. by a power. The power is right here as an exponent, and a power of 10. Now this number right here is not in scientific notation, and the reason it's not in scientific notation is because you have right here, this number is not between 1 and 10. This number is over 10. It's 23. So 23 times 10 to the fifth is not in proper scientific notation. So we somehow have to move the decimal and understand that the decimal is to the right of a whole number, so it would be right there. We need to move the decimal in such a way that we can get these two numbers to be between 1 and 10. So what I got to do is move the decimal that's understood to be there to in between the 2 and 3 right there. So 2.3, but now since I moved the decimal over, I need to add an exponent to that. And so that would now be 10 to the 6th. So that's our number that is in scientific notation. 2.3 times 10 to the 6th is the correct way to write that number that we had previously as 23 times 10 to the 5th. All right, so hopefully as we do these will make more sense. So here's a really big number. This number is 137 million. Okay, 137 million can be written this way. 1.37 times 10 to the 8th. Why? Because the decimal is understood to be right there. And then I got to count how many spaces I went over to the left. So that's over here. 1, 2, 3, 4, 5, 6, 7, 8. So it's 1.37 times 10 to the 8th. So that's how I write a really big number with scientific notation. And I can see that I'm going to have a 1 and a 3 and a 7, and then I have 6 more spaces to get to that 8. So here's 2 spaces, the 3 and the 7, and then I'm going to have 6 more zeros to get to 10 to the 8th power. All right, so now you give it a shot. Using scientific notation, rewrite the following numbers, and some of you can do this in your head, but some of you need to write it down. So I'm going to give you 32 seconds to do these 3, okay? In fact, I'm not going to give you 32 seconds. Siri is. Hey, Siri, set the timer for 32 seconds. Your timer is set for 32 seconds. She's timing you. All right, so let's see how you do on this one. Remember, you're going to count the number of times you need to move the decimal over in order to get a number between 1 and 10 as your mantissa. Okay. All right, so Siri is still timing, and your time is almost up, I think. What started this? Ah.
Shut the fuck up, faggot.
Oh my goodness. Hang on a second. All right, so that's nice. Hey, Zoom bomber, go home. Okay, so let's go back to screen share, and we'll get over to this one right here. If you, I can't see all of you because I'm on screen share. If you got 347,000, remember what you gotta do is move the decimal over and count how many times you move it over. So, what's your answer? Hopefully you got that. It was 3.47 times 10 to the 5th. All righty. All right, so I can see some of you.
We have a question.
Oh yeah, what's your question?
How'd you get like 10? How'd you get 10?
It's always 10.
Oh, it's always 10?
Yeah, so what you're gonna do is you're gonna move, count how many times you moved the decimal over. And I moved it over 5 times. And I moved it over to here and not here. And I moved it over to here and not here because what it is I needed to get that first number, this one right here, to be between 1 and 10. So as I move this over to the left, 1, 2, 3, 4, 5, I moved it over 5 times. So I got 3.47 times 10 to the fifth. Does that make sense, Oscar?
Yeah, thank you.
Okay, no problem. All right, so that's how that works. Let's go and take a look at the answers for the other two that we have here, because we're just learning how to do this. All right. Did you get this answer? 9.02 times 10 to the eighth. Can you give me a yes in the
Yeah.
participants if you got this? Or you can put a thumbs up if you want to. That's 9.02 times 10 to the eighth. Why? Again, for some of you who are just learning how to do this, you take this decimal and move it over 1, 2, 3, 4, 5, 6, 7, 8 times. Now, why couldn't I just stop right here? Well, if I stopped right here, it wouldn't be a number between 1 and 10. It'd be 90.2. So I would take one more, and it would go 9.02 times 10 to the eighth. Okay? And then this one here at the bottom is 6.14 times 10 to the fourth. Can I get a woot if you got that right? Oh, good, Dyra. All
I
right.
got it.
Hey, you got it. All right, good. So that means you guys are getting the hang of this, but we got to do more examples. Now, you can also go backwards. You can go from having a number in scientific notation and then going to standard form. So when you have this, you should get a normal number. So at this point, what you're doing now is you're moving the decimal back the other way. And the exponent tells you how many times you're moving the decimal over. So for the first one, it's 1.23 times 10 to the fifth. I'm going to move this decimal over to the right 5 times. So when I do that, it'd be 1.223, but then it'd be 12. That's moving it over once.
Yeah, 123,000.
Yeah, you got it. It'd be 123,000 because you move it over 5 times. Good job. All right, let's do the other one. Let's do the next one. 6.806 times 10 to the 6. Sometimes you're going to, after a while, you're going to be so good at this, you can do this in your head. Bam, I just got it. Okay, so hopefully you can do that soon too.
6,000.
Ooh, almost. It's going to be
That's what I
6,806,000.
said.
Oh, did you say 6 million?
Yeah, it says 6,800,000. 806,000.
Well, I misheard you, Sean. Good job. That is correct. 6,806,000. All right, so that's great. Let's go to the next one. Here's these. Give these a try, and I'll be with you in 42 seconds. All right, so try these. Put them on your paper, and we'll see what your answer is in just a moment. All right. Hey Siri, set the timer for 42 seconds.
Okay. Your timer is set for 20 seconds.
I said 42. All right, you're almost done anyway? I think that a lot of you are almost done. All right, so hang on. Unmute. All right, 4,000. You saw the answers already, but let's go ahead and take a look at them again. 4,000, and then you should be able to go back and forth at this point. So here's 4 times 10 to the third power. You know, you have a 4. You move this. This is a comma, not a decimal. So you move that over. Actually, no, the decimal's right here, and you move it over 3 times to get that 4 by itself. And then to use the scientific notation, remember what you gotta do is to go to standard form, move it over to the right 3 times. So that's 2,480. And then the next one is you gotta move the decimal over 6 times. That's gonna be 6,123,000. And then the last one, you're going to scientific notation. So you're gonna take this decimal on the right, and you're going to move it over 3, 6, 7, 8 times. So hopefully you got 3.06 times 10 to the 8. Good deal. All right. Now, in science, and especially physics and chemistry, it's not going to be correct unless you tell us what the answer is in units. So right here it says in the United States, 15 million households use private wells for their water supply. Write this number in scientific notation. So the number is going to be, remember the decimal points right there. Move that over, 3, 6, plus 1 is 7. So the number is 1.5 times 10 to the 7th, okay? But the unit is in households, okay? So especially in physics, I'll mark you wrong if you don't give us the units, because if because of that's you got to know how many of what. All right, going the other way, the United States has a total of 1.2916 times 10 to the 7th acres of land reserved for state parks. Seems like a lot, doesn't it? Write this in standard form. Well, hopefully you can see that what you can do is take this number and move the decimal over 7 times. So 1, 2, 3, 4, and then I got 3 more spaces to go, so I've got 3 zeros to add on, and that's what happened right here, 12,916,000 acres. All right, when you have a negative exponent, that gives you a really, really small number. So if you take a look at this here, you can see that 10,000 is 10 times 10 times 10 times 10. So that's 10 to the 4th power. It tells us how many zeros are in this number right here. Really, it's spaces. Okay, but and we saw that in our previous examples. When we have 1,000, that's 10 to the 3rd power. It's got 3 zeros. It's 10 times 10 times 10. When we have 100, it's 10 times 10. It's 10 to the 2nd power. And so you can see, hopefully, if you take a look at the exponents, you can see a pattern that's occurring. But you can take this even further, because if we go to a really small number like 1 to the 10th, or 1/10 of something, this is how we write it with exponents. 1/10 is 10 to the negative 1. So if this is 10 to the negative 1 with the 10 in the denominator of this fraction, then this is going to be 10 to the minus 2 power. And then 1 over 1,000 is going to be 10 to the negative 3rd power. And then 10 to the negative 4th power, you can see it's 4 zeros right there. It's 1 over 10 to the 4th, or we write 10 to the negative 4th. So let's try some examples of really small numbers. We have 0.00882, 0.0000059. You can see how hard that is to say, and 0.00004. So try those real quick, and then we'll see what you get for the answers. Can you give me a thumbs up or a yes in as a symbol when you are ready to roll? And when I see most of the room with a thumbs up or a green check mark yes, then we'll go on and give you the answers. I can see a couple of you have the answers already. That's good. Remember, you can do a thumbs up if you look at reaction, or you can do a yes if you go to participants and you check that in your Zoom control. All right, we're getting even more, so good. George, I see you, that's great. Anybody else? All right. Got some thumbs up now. All right, let's go on and let's take a look at the answers. This right here, I had to move it over 4 times to get a number between 1 and 10. That number is 8.82. And so it's 8.82 times, how many times did you need to move it over? I moved it over 4 times to the right. 1, 2, 3, 4. And that's how we got 8.82 times 10 to the 4th. Remember, this x is going to be the same for all these. This 10 is going to be the same. But what this tells us is that tells us what the mantissa is, the numbers that were important, that the numbers that were significant in our original number, and it tells us how many times we moved the decimal. Okay, sometimes we move the decimal to the left, sometimes we move it to the right. In this case, we're moving the decimal to the right. So this tells us that we moved the decimal to the right 4 times. This one, we're going to move the decimal to the right again, and so we're going to have a negative exponent. Remember, you have a negative exponent, it's going to be a really small number, less than 1. And so this one is 5.9 times 10 to the 7. How'd you get that? 5.9 is the number between 1 and 10. And how did we get the decimal right there? We moved it over 1, 2, 3, 4, 5, 6, 7 times. This negative tells us which way we moved the decimal to get there, from standard to scientific. If we move to the right, you're going to need a negative. If you move it to the left, like when you have a big number, then that's going to be a positive. And you don't have to put the plus there because it'll almost always be the positive. So it's understood to be there. It's like the default. If you don't have that negative, then you know it's positive. And then this one right here, this is, the answer is going back 4 times 10 to the negative 5th, moving over 1, 2, 3, 4, and you can't stop there because then your number would just be 0.4. Take it over one more time, it'd be 4 times 10 to the negative 5th. All right, here's some more examples, and let's do those even more quickly and see how you do on these. 0.004, number 2 and 3 are already in scientific notation, and you're changing those to standard. And then 4 and 5 are standard, and you're changing those to scientific notation. So take a moment and let's see if you can get the correct answer for those. Some of you are doing it in your head, which is fine as we practice, but you probably want a piece of scratch paper, and you're going to want to do that scratch paper. Okay, so I'll give you another half a minute to do just these 4 problems and move to decimal. Got 0.0004. All right, so let's take a look. What'd you get? And hopefully for number 1, you can see it's a really small number just looking at it. So you know it's going to be a negative exponent. And it looks like you move it over 4 times. So it's going to be a 4 times 10 to the negative 4. My number here, I'm going to a standard number, and when I need a really small number. So this tells me that I'm going to move this decimal over 6 times to get a small number. So I'm going to move this, actually this time, to the left. I'm going to move it over to the left 6 times so that I get 5 zeros. So it looks like this. Similarly, this is going to be a small number because it's negative. But I'm only going to move the decimal over 5 times instead of 6. There's already a 6 there. So if I move the decimal over 5 times, then I'm going to have 4 zeros. So it's going to be 0.0006123. And then over here, a small number, I need to get the scientific notation. How many times am I moving the decimal over to get a number between 1 and 10? That's 3.06 is the number I'm looking for. So how do I get there? 2, 4, 6. So I got 6 movements, and I have a really small number, so that's going to be negative. It's also negative because I moved from left to the right. So when I moved it to the right, that's a negative exponent, and I moved it over 6 times, so that's 3.06 times 10 to the 6. And over here, I'm moving this one over 4 times, so the answer is 8.92 times 10 to the negative 4th. You're going to get a lot of practice doing this. Your next assignment is a lot of these problems, but having done these, you can hopefully from our talk today, and as you go back and look at your notes, hopefully you can see how to do this. And If you need to, then go back and watch the video so that you can understand how to do these. This one is the nucleus of a human cell is about 7 times 10 to the negative 6 meters. In diameter, what is the length in standard notation? Remember, standard numbers don't have the exponent or the times 10. And so this is a really small number, and it's 10 to the negative 6. So I'm going to move the decimal over 6 times, 2, 4, 6. And that's how I got this answer right here. This is the length, 0.000007 meters. Here's another one. This is a really small part. And now we're going to scientific notation. And again, you can move this over 3, 6, 9 times. So my number between 1 and 10, the mantissa is 3. So this is 3 times 10 to the 9th. 10 to the negative 9th because it's a small number. And I move to the right. And then I also have meters. So I have the units there also. All right, a couple other things you need to know for the handout. When you multiply the mantissas, what you do is you add the exponents up, okay? More on this next time. So as you do the problems that you're probably, we'll go over this again when we start doing the problems with you. But what you're gonna do is you're gonna multiply these numbers together, 8.82 and 5.9. Multiply those two numbers together, and then these exponents, add the exponents together. Remember the x and the 10 are always going to be there. But if you take these numbers right here, when you're multiplying, that's 0.4 plus, negative 4 plus negative 7. That's going to be negative 11. So that's how I got that negative 11 right there. And then we take the mantissas and multiply those. We get 52. Except 52 is not a number between 1 and 10. So I got to move this decimal over to the left once. And when I move this decimal over to the left, I've got to change this to 10 to the negative 10th. So there's my answer like that. If you remember my discussion of significant figures, I also have 3 sig fig here and 2 sig fig here. And that's why our answer is going to be, even though you have 5 digits, your answer is going to be in 2 significant figures. Again, more on this as we practice this more and more. So that's the answer. And you remember you want to.
2 sig fig?
I said, say that again.
You said 2 sig figs or 5?
It's 2 sig fig because if you take a look over here, we started with 3 here and we have 2 here. Your answer should be in the lowest number of significant figures of the 2 things that you're multiplying together. So you've got 8.82 times 5.9. This one has 3. This one has 2. And that's how we got the 5.2 times 10 to the negative 10. Let's do one more division. And when you divide, it's similar. But what you're going to do is you're going to, well, let's show you. What you're going to do is divide the mantissas and subtract the exponents. So that's what you do when you divide. Here's my example. I'm going to divide these two numbers. But remember, the x and the 10 are the same. I'm going to take these numbers and I'm going to subtract these. Okay? So that's what's going on right there. I got 3 minus 5 is going to be negative 2. And then this is going to be 5 divided, almost 5 divided by a little bit over 3. So is that 1 point something 5? And so here it is. When you do it on a calculator, 1.5375. And then I got 3 and a 5. 3 minus 5 is negative 2. This one here has 3 sig fig. This one has 2 sig fig. So my answer is going to be 1.5 times 10 to the second. And you box your answer and you show your work. Okay? So now it's your turn. What you're going to do is you're going to take what you learned and first of all, finish up the Cornell notes, write the Cornell questions on the left, and then have at least 5.0 questions, plus write your summary at the very bottom of the page so that we know what we learned. And after you've done that, then you get started on the problem set. The problem set is not due until